Swayam Prabha. Digital India. Educated India.
As we know that so far we have studied the Ohm's law as the only law which we have applied for resistor, and we have seen that the voltage across the resistor is dependent upon the amount of current which is passing through the resistance R at a given temperature. So for time being, we'll assume throughout that the temperature is not varying, so we can apply the Ohm's law and find out the voltage across the resistors. But while it comes to the solving a circuit, we cannot use the Ohm's law alone, right? The Ohm's law which we have studied, we cannot utilize the Ohm's law and find out the voltage and current and different part of the circuit, because it deals with the particular element and which is insufficient to solve the circuit. So when the Ohm's law is utilized along with some other laws, such as one of the important law is Kirchhoff law. Okay, Kirchhoff's law. So if these two laws are used together, then definitely we have some hold on the circuit parameters, which is voltage and the current. So the Kirchhoff's law provides the two variants, you can say. One is for voltage and one is for current. So one by one we will see that what do I mean by the voltage current law, sorry, Kirchhoff current law. So first we'll see Kirchhoff's current law, which is nothing but the KCL. So it states that the algebraic sum of currents entering a node is, or in general, it is equal to the current which is leaving the node. So suppose there is a node, okay, the node A, and the current is coming and going. Okay, so I1, I2, I3, I4, I5. So this is a node which is represented by, suppose, N. So algebraic sum of all the currents entering to the node is 0. What it means that the current which is coming to the node is taken as positive, then the current which is leaving is taken as a negative. So suppose I1 is taken as a positive which is entering to the node, then algebraic sum I1, then I2 will be also positive, it is also entering, then I3 is leaving, so it is in negative polarity. Again we have I4 as a positive, sorry, it is also leaving, right? It is also negative, yes, correct. And then positive is which one? Yeah, I5. The total algebraic sum is nothing but the 0. Okay, so the total current is 0. So here I have written that the algebraic sum of the current entering to a node is 0. So if the polarity is not taken, then the current entering is equal to the sum of the current leaving, will be 0 for the current which is entering at some node. Suppose some circuit if I draw, okay, let us assume some older type of circuit where two loops with one source, and this is the approximate representation R1, R2, R3, the voltage V. So there is a node right here. The current which is entering from here, then it will go in this direction, then this direction. So suppose here it is I1 and here it is I2. So at this node, and the I3 is going in this branch. So the total current I1 is entering, it has to be negative. Then we have I3 also in the middle branch which is leaving. It has to be equal to 0. It means I3 is nothing but I1 minus I2. So whatever the current is coming here, it is going here and going here. So it is getting divided. And if you integrate both sides, suppose it is a function of time, I2t plus I3t, algebraically I am writing, is equal to 0. So all the currents coming to this point is 0, or it can be the net current. So the total algebraic sum of the current, okay, if suppose this is your node. Now in this particular node, suppose we have current, net current at node n. Okay, so the algebraic sum of the current at the node, not at the node n, is sigma I of t total is nothing but the I1 of t plus I2 of t plus In of t. Sorry, In of t is not written this way. In of t. Now in this particular case, if you see the total current and you integrate both sides, so it will become charge, right? Because I of t integration of dt is nothing but the q. Okay, so this we have seen from the earlier lecture. So if you integrate both sides, this will become the q total. We can write total charge if you write, then sigma is not required. So the total charge is nothing but the q1 of t plus q2 of t plus qn of. There are n branches which is coming to the node n. Oh, there is a confusion, right? This n, so you can make it as a m, I of m, and this also plus q of m. So m is the number of branches which is coming at the node n, and the total current at the node is it, algebraic sum. Then the total amount of charge is nothing but the integration of all these currents, which is corresponding to I1, I2 is Q1, Q2 or so. So keeping this in mind, we can say that the sum of the current entering to a node is equal to the sum of the current leaving, which I have said earlier. So before that we start, let us give an example of some circuit which is want to have an example. Okay, so we have a kind of some source here which is here. So this is I2. If suppose this is a DC thing, we can assume, right? So I1 is going this way, then suppose I2 is going this way, and then we have I3 which is going suppose on the top. So I3 here, I2 here, and I1 here, and IT is the total node at this current. So IT is leaving the current, right, at this node. And then we'll pay little attention. The total current IT will nothing be but it will be I1 because it is coming to the this node, then it is leaving I2, so minus I2, and then it is coming to, this is also coming to I3, so plus I3. So I3 is approaching node this, I1 is leaving, I2 is leaving, so this is the KCL at node N. Okay, so this is KCL. So we have applied the KCL by writing this equation where we have assumed that the total current or algebraic sum of the current is 0. So whatever the current which is entering to the node is equal to the current leaving the node. So at the node N, the current which is entering is nothing but the I1 and I3, and the node, and this is the same node, right? Voltage will not drop because there is no branch element connected to this. So all this line is the same node. So that at the same node the current I1 and I3 is entering, and I1 IT and I2 is leaving. So therefore after applying the KCL we can write this equation. So that is known as the KCL. Similarly, if we understand the voltage law, okay, now pay attention to some another Kirchhoff law, which is Kirchhoff's voltage law. It is represented as KVL. It states that the algebraic sum of all the voltages, the algebraic sum of all the voltage is equal to 0 in a closed loop. Okay, now understand this. So mathematically we can write that sum of all the voltage in a loop L is nothing but the 0. Suppose go back to our old circuit here in this circuit. So if you see in this particular circuit, there is different elements, right? And the node is here. So there are two independent loops, one this one, and one big loop, right, which is dependent. So now if you want to apply the KVL, we have to select one loop. Any loop you can take, dependent or independent, provided that it makes a closed loop. So whenever we talk a closed loop, so suppose we just change the ink to highlight that. So one loop is this one. So this is closed loop, and one closed loop is this one. Okay, and one closed loop is this one, the bigger one. Okay, so there are three closed loop, one inner one this right side wala, and one is complete full loop. So KVL says that in any closed loop, this algebraic sum of the voltages. Now using the KVL, we have to keep in mind that the voltage if we consider this as raising potential as a positive, then the voltage will be dropped across the resistance, and the drop of the voltage given as per the Ohm's law, V equal to I into R, the current entering to this, and R will be the voltage, which will be a drop, and then again if you see there is some drop, and then again it comes to this. Okay, now we'll see a circuit. Now assume we can illustrate the KVL by giving an example. So let us take an example. You have a DC source, then you connect it to a resistor, and then one more resistor, and then one more source, and then resistor, and then it is connected. Okay, so here you see R1, R2, and this is R3. This is V1, V2, and the polarity, suppose it is dropping and raising. So start from any point. Okay, suppose we are starting at this point from the loop. So this forms a closed loop, right? This complete thing forms a closed loop. Now starting from this point, if we say the rise in potential is positive, so we'll write the assumption what we assume that the potential rise is positive. Like in KCL, we have written that entering the node is negative and leaving the node is positive. So potential rise is positive and potential drop is considered as negative. So from here, if you see, from negative to positive, you have jumped. So this is rise, which is positive V1. Then there is like VR1, which is drop. Then VR2, which is again some drop. Then there is like a rise, and then there is like, if you can assume, VR3. Okay, so V1 minus VR1, because it's a drop in the direction of current, so we assume that the current of direction is this. This is nothing but the I. So VR1, then again we have a drop of VR2. Then in the current of direction we have raise in the potential by V2. Then it is a drop of VR3. It is equal to 0. It means that the total rise in the voltage is equal to total drop. That's what makes the complete loop of a circuit having a sum of algebraic sum of 0. Potential is in the loop, so that is nothing but the KVL. So we applied the KVL to this circuit. So this is how we have to apply the KVL, and but here we have to consider only one fact, that either you take this opposite also, doesn't matter. You can take this as a negative, then you have to take this as a positive. So this polarity depends upon the, you can choose any of the assumption. Like we have assumed the current entering to a node is positive, you can assume current entering to a node is negative as well. But then when opposite phenomena is happening, you have to change the polarity accordingly. So that idea you have to always keep in mind. Now suppose a part of the circuit, okay, for example, there is like one battery, one battery, one battery, one battery. So positive, negative, negative, positive, negative, positive, positive, negative. Okay, so this is V1, this is V2, this is V3, V4, and the total is V4. Does it make a loop? Now my question is, A and B, is it a complete loop? Is this a complete loop? How will you say is this a loop? So this is a loop. So first we see the circuit, right? You are seeing this. Now you just draw the circuit, right? Here we can have for our, because we wanted some space, so we have done. Now you pay some attention to this circuit. So we know node A, we know something is happening and it is connected, and then connected this. Now we connect that it is not visually connected, but we have known the potential difference between A and B, right? So it means that we know this is a loop, so this forms a loop. Okay, so now VAB is nothing but the V4. No, we can connect it VS, so that V4 should not get confused. So this is nothing but the VS. So here also we'll just change it. Okay, so we'll just change it to VS. Now VAB is nothing but the VS. So VAB, we know this is, so we can represent it is this also, right? So now it is visually looking as a complete loop. So whenever we know the potential between the two terminal, we can always assume that there is a branch connecting to that node or point A and B with some voltage source. with the rated potential difference. So VAB is Vs. So if we apply KVL, suppose we are starting from A, so V1 is a drop, positive to negative, right? If it is assuming the current direction, so this is nothing but a drop, so negative V1. Then V2 is a rise because it is going from negative to positive, so V2 is a rise, so plus V2. Then from negative to positive it is going, so it is a rising to V3 plus V3, and then we have a drop, positive to negative V4, so it is drop is negative V4, and then we have in the direction current rising as negative to positive Vs, so positive Vs is nothing but 0. This equation that relates the algebraic sum of the potential across a complete loop is forming a KVL equation. Now similarly, if there is multiple nodes and we try to put all the currents which is coming across that node or passing through that node, then algebraic sum is equal to 0. So these two laws are very essential for any circuit to be solved with the help of KVL, KCL using Ohm's law. So all of the three equations or the laws are employed together to solve a circuit. Okay, now we'll take one of the easiest circuit and try to see how we can use this law. So for example, we have a source which is connected to a battery, then one resistor, and then one more resistor. So it is a single loop circuit. So we have a resistance R1, R2, and the voltage V. So in the question it is given that, V is nothing but 20 volts, R1 is nothing but 2 ohm, and R2 is 3 ohm. So these are the given thing. Okay, so we assume, so first we assume that the current is flowing in this direction. Okay, from positive of the battery the current is leaving and it is coming to the negative direction, and it is forming a closed path, so current is having a path to flow. So first apply KVL. What we see that voltage V, from here if you start from the reference, the voltage V is arising, then we are having a drop VR1, which is nothing but the drop, positive to negative it is going VR1, and then VR2, okay, positive to negative, so minus VR2 is equal to 0. So from here we can say that V of R1 plus V of R2 is nothing but the V. So V R1 plus V R2 is nothing but 20. So this is the equation 1. Now applying Ohm's law. Ohm's law if we apply, V R1 is nothing but the I into R1, which means nothing but 5 of R1 is given as 2, right? So 2I. Then VR2 is nothing but I into R2. So this is 3I. Okay. Now I into R1 or VR1 is 2I, and I into R2, VR2 is nothing but 3I. So 2I1. Now using this A and B, so putting the values from A and B. Okay. Putting the values of A and B, 2I, this is not one, I1 is not there because there is single loop, so this should be only 2I plus 3I is equal to 20. So 5I equal to 20. Then we compute the current which is flowing in this circuit was 20 by 5 and nothing but the 4 ampere. Ampere is the unit of the current. So we know that now the current in the loop is 5 ampere. Now look at the circuit. So this is 20 volt, this is 2 ohm, this is 3 ohm, and the current which is flowing is nothing but the 5 ampere. This is I. Now if it is asked that what is the voltage drop across the R1, so can you compute this? So what is the voltage across R1, which can be directly find out from the equation A, right? Here, or apply simply the Ohm's law, that is also Ohm's law. So from equation A, the voltage across R1 is nothing but the I into R1, which is 4 into 2 is 8 volts, and V of R2 is nothing but the I into R2. From equation B, it is nothing but the 4 into 3, 12. Now you see 8 plus 12 is 20. The total drop 20, which is equal to 20. So this is the voltage across R1 and R2. This is how you solve the circuit. So in this circuit, you know the current flowing through this branch, then this branch, and this loop, and you know the voltage across this one and across this one. So you know everything about this circuit. Now we can say this, we have solved the circuit. So again, I'll just repeat that whenever we want to solve the circuit, we have to have the voltage at each node and the current passing through the each branch. So we have to always make sure these two quantities are matched. Okay, so whenever these two quantities are known, we say that circuit is solved. Okay, now consider another circuit where we will be having a 2 voltage source. Okay, and 2 voltage source, we'll see that how we are going to use these two laws. So for example, I'll have one circuit with dependent source, so that you have an idea of dependent source as well. So take at another example where you have one resistor, then it is connected to one, this is a diamond shape, right? So this is a dependent source. Okay, now we'll see what it is depending upon. Then we have ideal source, then here one source is connected, and then this is how it is happening. Now give the value. So this is as suppose 12 volt, this we can assume 4 ohm, and this is the dependent voltage source, which is depending upon the V0, and V0 is nothing but the voltage of this 6 ohm resistor. Okay, this is V0, and if you assume this current direction, this, see, I'll tell you one more thing here. The direction of the current depends upon you. You can choose any direction, but make sure that in the flow of direction, you are taking the voltage polarity in the proper manner. Suppose in the direction of current flow, the drop is positive, then the rise should be taken as negative. This only you should maintain, and the direction of current you can choose according to your wish. So now this was a dependent source which is depending upon another voltage of the circuit of this element. So this is basically a voltage dependent voltage source. This is a voltage source dependent upon the voltage. Now this is again ideal source of 4 volt. Okay, now start from this point. You can start from any point again. So solving this circuit, applying KVL. So from here, if you start, and we have assumed this direction, and rising voltage is taken as positive, so 12 is positive, then from here it is a drop. Okay, so drop we can take as the current is assumed as I, the drop is nothing but I into R, which is 4, So drop is negative. 4 into I is the voltage drop. Then plus or minus, it is again a drop of 2 V naught. Drop of 2 V naught. Then it is a rise of 4 volt plus 4 positive. Then again it is a rise of V naught, okay, plus V naught is nothing but how much? 0. So you have written as uh, 12 minus 4i minus 2 V naught. So minus because it is drop, okay, 4 is raised and V naught is raised, okay, fine. So this is nothing but the voltage, I mean the KVL you have written, right? KVL. Now there are two variables I and V naught, and we have only one equation. How can we solve that? No. Now applying Ohm's law, where we know V naught is across this and the current passing is I. So V naught is what? The drop is the voltage is rising in the direction of current. Okay. The voltage is rising in the direction of current, which is taken as positive. It means V naught is nothing but 6I, right? V naught is taken as 6I. With a negative sign, because the resistance is a drop voltage drop element. So we'll solve this circuit now. So no, this I basically, sorry for this, this I is nothing but the capital I. Okay. So in the direction of the current, see, suppose this was the resistance 4 ohm, right? So when the current is flowing in this direction, the voltage is drop across the resistor is this polarity, like voltage is entering at the positive polarity. But here if you see, the I is entering at the negative polarity of this V naught. So V naught is nothing but minus 6 of I. So this is why this is equation number 2 and this is equation number 1. Now from 2 we'll put this value in this. So 12. So from equation 2 put the value of V naught in equation 1. So 12 minus 4I minus this not 1, 4I minus 2 into minus 6 of I minus k 6 of I plus 4. So if you solve this circuit, this will be for 12 and 4 16 together, and 4 or 6 10 and 12 8. So but means 2 only, right? So 16 plus 2 of I is equal to 0. So I is nothing but minus 8 ampere. So what do you mean by minus 8 ampere? You have solved this circuit and got a current negative. It means that the current is not flowing in this direction. Okay, the actual current is flowing in this direction with a magnitude of 8 ampere or minus 8 ampere in this direction. This is what it means. So polarity of the negative means that the direction of the current, which we assumed earlier before starting the question, is not the correct direction and it is opposite to the assumed direction. So this is what the negative signifies. Okay, so this is how you are going to take care of the here you have seen the dependent source. So dependent source, we get an extra equations so that we can relate the voltage and the current depending upon the other elements. If it is a current dependent source or a voltage dependent source, we get a extra equation to solve this. So we'll be seeing this more into the assignment questions or quiz question, how to solve these circuits. So now let us assume one current source or a dependent current source and see how we can use this KCL now. So one assume circuit, one resistor is connected, and that resistor is nothing but the 4 ohm. Okay, and then we have a current of 3 ampere, and then it is connected to a this source, and it is connected here. So this is basically dependent current source, but on what? So suppose a current I0 is flowing through this, and this is shown as 0.5 I0. It means that the current is flowing and the source is depending upon the another current, right? The other current is I0. So the another current 0.5 times is the value of this current source. So this is basically current dependent current source or current controlled current source. Okay, this is 4 ohm and the voltage polarity is V0. So we have to find the value of V0 and I0. This is the question. So when we try to again like what we can do, so the node at which this is connected, sorry, this node. So look about the total current which is appearing. So applying KCL at node, suppose it is node N. So this is node N. So the total current entering is 0.5 I0. Then the current is leaving, right? Then minus I0. Then again current entering is 3 ampere, which is total sum should be 0. So it means that 0.5, the current entering is 0.5, and the current leaving is this. Okay, so I0 minus 2.5 I0 is 3. So I0 is nothing but the 3 by 2.5. Sorry, I made some mistake. So not this way. So this will be basically minus 0.5 I0 is equal to 3. So I0 is nothing but 3 by 0.5, nothing but 6 amp. So this is the thing. And what is the V0? V0 is nothing but the I0 into R0. 6 into 4, 24 volt. So this is basically the Ohm's law, and this is basically the KCL. So Ohm's law, in addition to the KCL and KVL, is very useful in using the mathematical understanding so that we can utilize the